Now, to overcome the violation of kind of our Gaussian linear model assumptions, we're going to fit a generalized linear model to these data. And the specific type of generalized linear model we're going to fit is called a log normal model, a log normal generalized linear model. This type of GLM is one that assumes that the residuals are still normally distributed, just like a regular linear model. Residuals will be Gaussian distributed. But the reason it's called a log normal model is that it changes the deterministic part of the model. The stochastic part of the model is still distributed as a normal distribution, as I said, but the deterministic part is now actually log transformed so that the values can't be negative. You'll see how this works in a second, but first let's fit the model. Let's call it the tibial plateau breadth model, tpb.mod. Now, to fit a GLM, we use, instead of the LM function, we use the GLM function. If you pull up the help page for this, you can see all of the different arguments it takes, examples of how to use it. And what we're going to feed it is LTPB as a function of Krull, data equals Goldman. Again, this should look familiar. Right up to this point, it's the exact same as what we tell a linear model. But now things get a little bit different because we need an additional argument. What we need to specify here in the GLM argument when we're trying to make a log normal model is family equals Gaussian, open parentheses, link equals log. Let me put that on a new line so you can see it a little bit more clearly. So, in this GLM function, we're saying, all right, we're going to inspect LTPB as a function of the Krull index from the Goldman data, right? And in that model, in this GLM that we're making, we want the family to be Gaussian. What this means is that we assume the errors, the residuals of our model, are Gaussian distributed. The family argument here is referring to your error distribution. All right, it's referring to how the points, your residuals, are distributed around your model fit line. In this specific case, we're using a Gaussian distribution. These measurement data, right, they're continuous. They're going to resemble Gaussian data in a lot of ways. We can say that the residuals are going to be normally distributed and most likely be able to get away with that. Sometimes you can't, and you'll have to use other distributions, but for now we're going to use a log normal one, and it looks like this. Now, there's another part to this too. The family is Gaussian. That's the error distribution. But then we also have in parentheses after that link equals log. And what this is, the link function, is a transformation that's applied to your deterministic part of the model. It is that function that you wrap around the values that you're predicting in the deterministic model equation. And that function in this case is a log function. We're going to take a logarithm of that kind of model fit line. This is kind of what separates generalized linear models from linear models, right? As we've said in our lecture on GLMs, the difference is really just that there's this extra kind of abstraction from a linear model, that a linear model is really just a specific type of GLM. And so if we wanted to actually make a linear model, we would say GLM, family equals Gaussian, link equals identity, where the identity link function just means that whatever value you put in is the same value you get back out. That would actually be an LM. If I said GLM, LTPB as a function of Krull, family equals Gaussian, link equals identity, I wouldn't even need to make this a GLM because that's the same thing as an LM. That's what the LM function does. But here we don't want link to be equal to identity. Link is log in this case. Our link function that we're using to transform the data is a logarithm. And the reason we're doing that is because a logarithm allows us to take data that are bounded by 0 and extend to positive infinity, right, and transform them onto the scale of the Gaussian distribution. Right? If you'll recall, the Gaussian distribution, the normal distribution, runs from negative infinity to positive infinity. But our measurement data here run from 0 to positive infinity. They can't be negative. What happens if you take the log of 0, our lower boundary for our data that we're working with here? If we run that, we see the answer is negative infinity. Right? Let's take the log, then, of infinity. And what do we get? Infinity. Right? The log of infinity is infinity. The log of 0 is negative infinity. 0 and positive infinity, as I've plugged in right here, those are the boundaries, right? The bounds of our measurement data that we're trying to model. And the results of logging those two boundaries, negative infinity and positive infinity, those are the boundaries of a Gaussian distribution, right? So this log link function that we're applying to our GLM is allowing us to take our measurement data, which are bounded by 0, and kind of unbound them, in a sense. It translates them onto a Gaussian scale. And this is why GLMs are so useful, so powerful, and just so cool, is that you can apply these link functions, right, and change the very shape of the model fit that you're producing. And it does that through a certain set of functions, in this case, the logarithm function. And so if we have this GLM now, we can plot the diagnostic plots, but they're going to look the same as before, right? And it's important when you're looking at diagnostic plots for a GLM that you keep that in mind, right? The diagnostic plots, this plot model function, that it's really meant to be used for LMs, right? GLMs are, by definition, going to violate a lot of these assumptions, and so a lot of people won't even really look much at these diagnostic plots for GLMs. Here, let's do it, just so I can show you what's going on. But in this case, it's looking the same as the kind of first plots that we pulled up, right? Because for the kind of shape of the model that's right around the data, it's very similar to a regular LM function. Our residuals plot here looks the same as before, pretty much. Very good. QQ plot, again, we've got some deviations from normality a bit at high and low values, but it's not terrible. No clear heteroscedasticity here, and no undue influence of certain points over others. I do want to go back, though, and show you kind of, there's a weird pattern going on here. Look at this implied line between these points kind of curving up there, and then there's another one curving down here. This was in the first set of diagnostic plots I showed you too. You can see these implied lines in the points. And if I go back then to the first plot as well, you can also see a bit, if I were to kind of zoom in here, there are some implied lines in here too, if you look closely enough, just running horizontally now. What's going on here? Whenever you see patterns like that, right, this is where it's really apparent. Look at that. That sort of pattern there, that's telling me that something funky is going on. This could be a sign that our residuals are not independent of each other, or it could be a sign that there's some other weird assumption being violated. In this case, what's actually going on, I think, is that the measurements of LTPB are not actually continuous as much as we think they are. PB, let's run that and look at these. See that everything is kind of something 0.0, something 0.0. A handful of 0.5s in there, but they're mostly all 0.0. So in actuality, while these are continuous measurements that could take decimal places, they were calculated kind of at a level, and because they're in millimeters, very small numbers, they're rounding errors. That's what I think is causing the weird shapes in the residuals. So when you see something like that, think about what's going on in your data. Here, I don't think it's anything really problematic. It's just that there's rounding error going on, and so I'm willing to proceed as is with that. I don't think we're violating any bad assumptions. But of course, we are violating the assumptions that we know we're violating because we've got measurement data. And so there's some inherently kind of violated assumptions here. But of course, with these diagnostic plots, things are looking okay. Our GLM is looking pretty good. But now let's actually move on from building the GLM, now that we understand kind of what the family argument is and what the link function is, and let's start plotting the GLM.